All right, so this is Bridge Scour by James Norris. What is bridge scour? Bridge scour is the process of erosion or removal of sediment, such as sand and rocks, from around bridge abutments or piers that's caused by swiftly moving water. It's the leading cause of bridge failure globally and presents a critical challenge in infrastructure, particularly in areas that are prone to flooding, have heavy rainfall, or strong river currents. A few problems that are associated with bridge scour. There's structural weakening. Obviously, erosion undermines the foundations of bridge piers and abutments, and this leads to instability and potential collapse. There's a public safety risk. Bridge failure due to scour poses significant risks to public safety, especially in high traffic areas. There's economic impacts. Repairing or replacing damaged bridges will cause or will have substantial costs associated with it, and it can disrupt transport networks. There's environmental concerns. These scour events can alter riverbeds and aquatic ecosystems, which impacts local biodiversity, and and it can cause climate change as well. While solutions for mitigating bridge scour are effective, their implementation is often subject to significant economic constraints. These constraints can influence decision-making, prioritization, and execution, particularly for developing regions or budget-limited projects. Um, so here are a few of the key economic challenges. There's high initial costs. As far as the engineering solutions, advanced interventions like installing riprap, bed armoring, or caissons, obviously, or they involve significant material, labor, and equipment costs. Um, there's maintenance and monitoring expenses, real-time monitoring systems like sonar devices. They have ongoing operational and maintenance costs. And there's funding limits. Government agencies a lot of times have limited budgets, which need to be distributed evenly across a variety of infrastructure needs. And private sector involvement, attracting private investment for scour mitigation can be tough because it can't be directly monetized. So all these economic constraints, they can lead to prioritization of short-term fixes over long-term fixes, which leaves more bridges vulnerable to future scour events. Um, Ethical considerations in addressing bridge scour revolve around environmental protection, community impacts, and the responsible allocation of resources. Scour countermeasures such as riprap or channel modifications can disrupt aquatic ecosystems by altering flow patterns, sediment transport, or habitat conditions. Ethical design demands minim that minimize harm to local flora and fauna while complying with environmental regulations, like the Clean Water Act in the U.S. And there's obviously the community and safety aspects. There's an ethical responsibility that's required when prioritizing public safety by implementing timely and effective solutions to prevent bridge failures, which could result in significant loss of life and property. Timeline constraints in addressing bridge scour are influenced by several factors and can limit how quickly solutions can be implemented. There are emergency repairs and preventative measures that need to be taken. You often have to wait for permitting and environmental approvals. And then there's also construction schedules and seasonal constraints that you have to look out for. On top of this, there's also constructability constraints. Restraints for bridge scour solutions arise from factors that hinder the feasibility and efficiency of implementing designs. Some of these challenges are site accessibility. So a lot of bridges are located in remote or waterlogged areas, which can make it difficult to transport materials and equipment for the site. There's also water flow conditions that you have to look out for, like high flow velocities, tides, or flood conditions during construction can endanger workers and equipment, which can make it difficult to implement certain scour countermeasures. And then as far as some of the methods for solving bridge scour, the 2024 Florida Department of Transportation, or FDOT, Bridge Scour Manual provides updated methodologies and recommendations for managing and mitigating bridge scour. So the first of these is a hydraulic and sediment analysis. This can be used to predict scour depths under various conditions, and methods such as the Shepherd's pure scour equations can be used to account for the movement of sediment and site-specific flow dynamics. And pictured here, we have a diagram of a horseshoe vortex. Most bridge scour is caused by this, and it's created by the bridge support. So it's important to be able to identify this when attempting to solve bridge scour. Um, there's also foundation adaptations. The FDOT manual advocates for designs that incorporate deeper foundations, such as driven piles or drilled shafts, which are less susceptible to scour. Foundations and in erosion resistant materials like rock or clay are analyzed using the Florida rock clay scour procedure, which integrates shear stress resistance into long-term scour evaluations. FDOT also recommends retrofitting older bridges with scour-resistant features like haulers or sacrificial piles for extreme cases, relocating piers or bridges to less vulnerable locations or elevating bridge spans above maximum flood levels may be necessary. Um, and then monitoring and inspection, real-time monitoring tools such as sonar-based scour sensors and periodic hydrographic surveys are essential for detecting and responding to active scour conditions promptly. So next is the design process for a solution to bridge scour. So overall, the most effective solution to bridge scour is installing riprap for bridge scour mitigation. So designing riprap in accordance with the FDOT guidelines involves a series of specific steps to ensure that the riprap provides effective protection against erosion and scour that's caused by river or stream flow. Here's a quick overview of the process, which includes calculations that are used to determine the appropriate rock sizes and gradation. So the first step is hydrological and hydraulic analysis. So before we can start designing the riprap, it's important to perform hydraulic calculations to determine flow conditions, including maximum velocity and flow depth at the bridge site. And the flow velocity can be computed using Manning's equation, which is listed here, where we have V is velocity in feet per second, N is the roughness coefficient, R is the hydraulic radius, and S is the channel slope. Next is the riprap size selection. So before we can start designing, we have to calculate the size of the stone necessary to withstand the flow without being displaced. And this is typically done using the stable rock size equation, which is listed here. So in the equation, we have the medium diameter of riprap, Q for discharge, Vs, which is the velocity which we got from the previous equation, and W is the width of flow. And then step 3, we have gradation and placement. So specifications from FDOT provide certain gradation requirements for the riprap materials. The materials have to meet specified criteria, which varies by project and situation. During the placement, the riprap stones are typically laid in a series of layers with thickness that's calculated based on the flow volume and stable rock size calculations. The riprap should be placed with care to avoid uneven layering and ensuring that the structure is tightly packed to prevent shifting. Fourth step is the bedding stone and geotextile fabric placement. So bedding stone is required beneath the riprap to provide additional stability. The gradation of bedding stone typically includes stones from 12 to 1 inches in diameter. Geotextile fabric is often placed between the stone and the riprap to prevent soil movement, and it filters out fines, which preserves the integrity of the riprap. Step 5 is quality control and material selection. So the FDOT standards specify that materials like broken stone or broken concrete must meet certain physical properties, such as a maximum absorption rate of 5% and a Los Angeles abrasion loss that isn't over 45%, and a soundness criteria that is based on sodium sulfate testing. This process ensures the riprap is robust enough to withstand the forces acting on it and provides long-term protection for bridge foundations against scour and erosion. And then sixth, after the riprap is properly installed, you should probably routinely inspect it. Install a sonar that detects bridge scour conditions, and having someone inspect it routinely. And then a completed riprap will look like this picture here. Riprap is widely used to mitigate bridge scour because of its effectiveness in reducing erosion around bridge piers and abutments that's caused by flowing water. Here's a detailed explanation of why riprap is a very effective solution. So first, it dissipates flow energy. Riprap consists of large angular stones placed strategically around bridge foundations. These stones absorb and dissipate the kinetic energy of flowing water, which reduces the water's velocity near the riverbed. By slowing down the water around bridge piers or abutments, riprap minimizes the erosive forces responsible for scouring. Next, it stabilizes the bed and banks. The placement of riprap creates a protective layer that prevents the riverbed and riverbanks from being eroded by turbulent flows. It acts like a barrier, which holds off sediment in place, and reduces the likelihood of deep scour holes forming. It's very adaptable to flow dynamics. Riprap is particularly effective because of its ability to self-adjust under changing flow conditions. When minor movements occur due to high flows, the stones tend to settle into a more stable configuration, which enhances their protective capabilities. This flexibility makes riprap a very resilient and long-lasting solution. Riprap enhances hydraulic performance by altering flow patterns around bridge structures. Riprap can reduce turbulence and vortexes that contribute to scouring. This redirection and stabilization of flow prevents the amplification of erosive forces. It's very cost effective and easy to install. Uh, Riprap is particularly inexpensive compared to other solutions. Um, and it's also very easy to install and maintain, which makes it a very practical choice for bridge foundations in a variety of environments. It's very durable in extreme conditions. The angular weight and shape of riprap stones resist displacement by strong currents. Properly designed and placed riprap can withstand extreme weather conditions, floods, and seasonal variations in flow rates, which provides long-term protection against scour. It's the environmentally friendly option for solving bridge scour. So riprap integrates well with the natural environment. It allows water to infiltrate and flow through the gaps between the stones. It reduces runoff and encourages sediment deposition in some cases. This permeability can foster vegetation growth, further stabilizing the riverbanks and improving ecological conditions. Even though riprap is very effective, it still has its limitations, and there are some things that need to be considered. One of these things is stone size and material. The stones have to be large and angular enough to resist movement, but not so large that they're difficult to install. As far as the placement, riprap has to be installed with careful attention to river dynamics to avoid undercutting or displacement. There's some maintenance involved. Periodic inspections are needed to identify and repair displaced stones or areas of insufficient coverage. So overall, riprap is a very effective solution for mitigating bridge scour due to its ability to dissipate flow energy, stabilize riverbed and riverbanks, adapt to varying flow conditions, and providing a durable and cost-effective defense against erosion. Proper design, placement, and maintenance are critical to ensuring its long-term effectiveness. So to conclude, bridge scour will always be a challenge for engineers when maintaining the safety of bridge structures, especially in areas that experience high amounts of water flow and sediment transport. After the evaluation of several different bridge scour solutions, riprap was chosen as the best overall countermeasure. Riprap consists of carefully placed layers of rock around bridge foundations and is effective in lessening hydraulic energy and protecting from erosion. Being that riprap is cost-effective, easy to install, and adaptable, it's an ideal choice for many bridge projects. So by implementing well-designed scour solutions and conducting regular maintenance and monitoring, the safety and durability of bridges and piers can be improved, which will ensure long-term functionality and protection from hydraulic challenges.